We live in a world that's secretly governed by a hidden architecture. It's this invisible set of rules that completely dictates how all the systems we rely on actually behave. Well, today, we're going to uncover a rather unsettling reality about our modern world. We're going to observe the hidden forces that make our systems function, and eventually, absolutely force them to stop. So, there's this universally accepted belief in engineering and system design. You've probably heard it. It's the idea that redundancy creates safety. We naturally assume that by backing up our systems, building alternate pathways, and designing components to shift their loads when they get stressed, we're keeping our networks secure, right? We literally build in backups to prevent a collapse. But actually, there is a terrifying contradiction hidden right inside this design, because under the right structural conditions, redundancy basically guarantees global collapse. The exact mechanisms that were designed to save the system are the very things ensuring its total destruction. To understand why this happens, we need to take a look at how physical forces behave when they're bound together. Let's consider a really simple physical structure. Picture a suspended walkway held up in the air by a row of vertical suspension rods. The design here is completely rational. The weight of that walkway is distributed evenly across all the materials. Every single rod shares the burden. It's a perfect architecture of mutual support. But watch what happens when we introduce a stressor. Say one vertical rod reaches its absolute breaking point. It fractures. Now, the walkway doesn't instantly crash to the ground. The system attempts to, survive. In a purely rational, localized adjustment, that broken rod just shifts its massive burden over to its immediate neighbor. And that single rational adjustment, it seals the fate of the entire structure. See, the neighboring rod was already carrying its own capacity. Now, it's taking on double the load. So it snaps. The load transfers again. And what we observe is this sequential snapping of adjacent rods. It's like a zipper effect. That local optimization, the shifting of weight just to survive, inevitably destroys the entire structure. There's just no reversing that momentum once it gets going. Okay, now let's zoom out from physical steel to the invisible infrastructure of our modern world. Think about computer networks, the internet, for example. When a critical router, a major node in the network, goes down, the whole system doesn't just halt. Just like those steel rods, it seamlessly bypasses the downed node to keep the traffic flowing. It shifts the load to survive. All that traffic is instantly routed to an alternative path, but a really familiar constraint emerges here. That alternative route was designed for normal traffic, right? Not a sudden, impossible deluge of redirected data. So the new path becomes entirely overloaded, it slows down, it struggles, and then it too drops completely offline. So we're left with this chilling contradiction. The network is behaving exactly as it was programmed to. The nodes are isolating the failure and redirecting traffic just to stay alive. Yet, that safety mechanism is actively propagating the failure. The system's own defense is literally the weapon destroying it. And this behavioral constraint isn't just limited to computer networks or suspended walkways. It scales endlessly. We saw it back in 1965 when the Northeast power grid collapsed. We saw it in the 2003 Italy blackout, leaving millions totally in the dark. We even witnessed it in the financial markets during the 2010 flash crash. Automated trading systems made rational decisions to shift loads and liquidate assets, which caused a trillion-dollar market collapse in mere minutes. This fragility is universal. The loss of alternatives is absolute. Before we continue, there is actually a quieter way to engage with all of the world's complexity. Sift is a news app I built. It provides a much calmer way to stay informed, highlighting only the most important news and completely avoiding those endless, sensational headlines. You can find it through the link in the description. All right, so when a power grid collapses or a massive market crashes, we usually look for human error. We look for a villain or maybe a software glitch. But the behaviors we're observing right now are not accidents. There is no villain. The structure itself forces the outcome. We are essentially watching the inescapable physics of modern architecture play out in real time. To really understand this inevitability, we have to look at the hidden mechanisms at play here. When components are so heavily interdependent that a change in one instantly forces a change in another, we're observing what's called tight coupling. In a tightly coupled system, there's absolutely no slack. There's no buffer for error. The dependency is absolute. And that means any local shock is instantly transmitted through the entire network. Now, as that shock travels, it encounters a second mechanism. It's a structural reaction that actually magnifies and perpetuates the change. Think about it, those rational local decisions, like a node shifting its traffic or a steel rod shedding its weight, they feed right back into the system and get amplified into unstoppable global events. The harder the system tries to stabilize itself, the faster it accelerates its own destruction. It's a positive feedback loop. So when extreme interdependence and this aggressive amplification combine under stress, we finally have a name for the phenomenon we've been watching this whole time: a cascading failure. It's a progressive collapse triggered by interconnected overloads. It ripples through the system exactly like a wave, growing larger and way more destructive with every single node it consumes. Now, you might be wondering, why don't we just stop it? Why not build a giant kill switch? Well, this comparison reveals the ultimate physical constraint. In a massive electrical grid, operators are constantly monitoring the system to prevent overloads. But the warning data, that control signal, travels through fiber optic cables and wires. It travels at the speed of light. The problem is, the electrical failure itself also travels at the exact same speed. The warning can literally never outrun the disaster. Because that control signal can't outpace the cascade, preventing the collapse from within the system is completely unachievable. You just can't isolate an outage if the power surge arrives at the exact same millisecond as your alert. Once that structural threshold is crossed, human intervention becomes a physical impossibility. Escape is quite literally mathematically impossible. And yet, as a society, we just keep increasing the stakes. We link these completely distinct, massive infrastructures together to try and increase efficiency. Just consider the relationship between the power grid and the telecom network, two completely different, highly critical architectures. The power grid desperately needs the telecom network's communication data to balance its electrical loads, and the telecom network requires the electrical grid's power to run its servers. They rely entirely on one another. Just observe the devastating lock-in of this design. If a cascading failure strikes the electrical grid, a whole region loses power. Instantly, the telecom network in that region fails due to a lack of electricity. But without the telecom network, operators are suddenly flying blind. They have no communication data to reroute power and manage the rest of the grid. The lack of power kills the exact communication needed to restore that power. It's an infinite, irreversible loop of failure. So we've arrived at the inescapable conclusion of complex architecture. The suspension rod tried to shed its weight to survive. The internet router tried to bypass traffic to maintain data flow. The power grid shut down a transmission line to prevent a fire. Every single component did exactly what it was perfectly designed to do: pure, rational, local optimization. Yet total global collapse was the locked-in result. Which leads us to a final, profound realization. When we look at the ruins of a collapsed network, a massive blackout, or a shattered financial market, we aren't looking at a broken system. The components didn't malfunction. The system was never failing. It was following its structure. Which leaves us with one final unsettling question. What other flawless structures have we built just waiting for the perfect moment to collapse?